Well, hello, everybody. Hope you can hear me.
Yes.
Okay, very good. Um, Let me bring up my slides. I can never tell if people are out there can hear me. Okay. 180A. There we go. Ah, and and you can see my slides. Okay. All right. I want to go over the first assignment, and I know that some of you learned some interesting facts about C++ expressions when you did this assignment, and that was the whole purpose. Okay, let me bring up Eclipse 180A. Okay, so I know several of you were caught by this problem. Okay, the division operator, okay, which is a slash, okay? Now, the way it works is that if both operands of the slash operator are integer, constants or variables, then the result of the division will be integer, and any fractional amount is truncated, just dropped off. So for example, 7 divided by 3 is going to equal 2. And 1 divided by 2 will give you 0, okay? No matter how close the fraction is to the next whole number, it will be dropped off. So even if it's 2.99999, if it's meant to be integer, the answer will be 2, okay? So now, many of you thought that because the variable on the left-hand side of the assignment is a double, that the right-hand side should be a double. No, the way C++ works is that it evaluates the right-hand side, and whatever answer you get is assigned to the variable on the left-hand side. Okay, so if you have integer division on the right-hand side, you're going to get an integer result. Okay, and that's why some of you could not get a value that was close to pi because the way you had coded the formula was wrong. Okay, now if one or both operands are double constants or variables, then the result will be double. So in this 7 divided by 3, if we made just one of them, either the 7 or the 3, into a double constant, which means that it has to have a decimal point, then the result will be um, a real number. And then here we made them both double, then we will get a double result. Okay, so that is something we all learned the hard way. Okay, now in general, the lesson is that you have to be very careful when you copy formulas out of a book or off a web, because the mathematical formulas are not necessarily the best computational formulas. And it's beyond the scope of this class, but there are courses on numerical analysis or scientific programming where you learn how to write your computational formulas in a way that you don't have a lot of round off errors, or you want to make the loop as efficient as possible. Okay, it's very dangerous if you have a loop that does a lot of these floating point calculations, because you'll get an accumulation of round off errors, and eventually your entire result will be wrong, because the round off errors have overwhelmed any correct values you may have calculated. Okay, so that's something that you will have to learn about if you're going to be doing a lot of mathematical type of uh, programs. Okay? All right, so here is the first formula. That does not require a loop. It's just a straight formula. And so you can see here, now you may wonder about this. Well, the square root function returns a double. And so this will be an integer divided by a double. So const 1 will be a double value. And then here, we're basically just calculating the various parts of the formula. And we have to take the natural logarithm of this quantity here. And there, of course, is a natural logarithm function. It's log and not ln. And we get the estimate, okay? Actually, let me...
I have a quick question.
Yes.
I wasn't sure if you already mentioned this, but what happens in terms of like typecasting, like if, or in terms of the types, if you like declare like double const 1 equals 12 divided by 5, since you declare it as a double, does it give like a double answer, or does it, or because since both of the values are integers, does it make it an integer?
Well, okay, so again, whenever you have an assignment statement like this, it always evaluates the right-hand side, regardless of the type of the left-hand side, and whatever you get as an answer will be assigned to the variable on the left-hand side of the assignment, okay? Now, a lot of students thought that, well, because the left-hand side is a double, then you should always get a double on the right-hand side. Well, no, you can actually get an integer value on the right-hand side. And of course, if you do something like 7 divided by 3 or 1 divided by 2, or equivalent using integer variables, the result of the division will always be an integer, okay? And okay, let's say you assigned 7 divided by 3 to a double variable. Okay, well, first of all, we evaluate 7 divided by 3 and get integer 2. And when you assign it to a double variable, it becomes 2.0. Okay, so you've still lost the fraction.
Okay, thank you.
Yeah, so it always evaluates the right-hand side and then assigns the value to the left-hand side, okay? All right, so here we have the log function. Now I was going to actually bring up my code. See, I wrote the factorial function for you. Now, let me point out what I had in code check. Okay, you may have wondered why for each of the functions, I first had a declaration like this. Okay, there was no actual code, just the header, and then each one of these headers was preceded by a comment. Okay, so this is a programming style where you first declare all the functions. Declaring means you basically say, what's the name of the function? What is its return type? What parameters does it take? But then you don't actually write the code for the function, okay? And then you have a comment that describes what the function does. Now, the comment here is also an industry standard. It starts out with the / and then 2 stars, okay? And well, actually, let me just show you. Let me just make up a function here. I just call it double foo, and it takes an int I. Okay, I'm just making up something. Whoops. And okay, and so now what we want to do is put a comment up above it. So we could /**. Okay, and see, Eclipse knows that you're trying to put this comment above a function definition, so it automatically sets it up for you. And then, I can say whatever I want, compute foo, and then these @param and @return are also industry standard. And I'll tell you in a second why you want to use these param I some integer value, and then let's say it returns some return, not returns, some double. Boy, I really cannot type today. Okay, so this is standard way of commenting your functions. Now, after you've declared the function, all your function declarations, then you have the main. So here's my main, okay? And I guess we could have, main, okay, something like that. And then after the main, you have the actual definitions. Okay, so way up here, I had factorial declared, okay, and then I actually have the definition of factorial, okay. Now, we don't repeat the comment at the top, okay, so here's the actual code for computing the factorial, okay. Now, you can have comments inside the code. Let's see if I actually did that. I don't know if I actually had a, okay. Inside the function, you might put some comments to explain what it is you're doing, okay? Like I could have said in here, alternate adding and subtracting the term, okay? But you don't repeat the comment on top of the function, okay? Now, why do you use these at sign things, okay? Well, it turns out there are some utility programs that will read in your source program and then prepare it for publication, okay? And it will then do something nice with these. So these are like control keywords that will tell these utility programs that, okay, maybe print a comment in a special font or something. And the fact that you always start these comments with /** will indicate to these utility programs that this is a comment that describes how a function is going to, describes what a function is going to do, okay? So if you stick with these industry standards, then it gives you the option of being able to use these utility programs to prepare your program for publication. Like, maybe you're publishing the program in a technical article, then it's nice to be able to follow the industry standards, okay? All right, so let me get rid of this. Okay, now let's take a look at my Ramanujan 0. Okay, so of course it comes after the main, and here it is. Okay, so now it is calling the built-in square root function, and it's calling the built-in log function. Okay, and both of those require that you include the CMath library. Okay, so then, well, actually you're including the headers, that you're actually including the declarations of square root and log. Okay, that's inside CMath. Okay, this comes as part of the C++ installation. Okay, and then you have to say using namespace, because the names log and square root live in the standard namespace. So you have to tell the compiler that, hey, I'm using the standard namespace, so that later on, if you encounter like square root, okay, then well, first of all, you defined what square root is because you've included CMath, and then the name itself, okay, that you've defined up here lives in the standard namespace, okay. So this is kind of like boilerplate code that you always have at the top of your program. You will probably always have using namespace, okay, using namespace standard, okay. And then depending on what built-in functions you call, then you would have different includes. So here we're being very math oriented, and so we have CMath. Now IOStream and IOManip allow us to do output, okay? So when we do cout, then that's going to require IOStream, okay? And IOManip, that is required if you're trying to specify how many digits of precision and so forth. That comes out of IOManip, okay? I think we'll run into those in a second, okay? All right, so the first one is doesn't require a loop, it's just a straight formula, okay? Ramanujan was a very interesting character, Indian mathematician who was active during the early part of the 20th century. And he was this genius that just came up with all these formulas for calculating pi. And you know, I would look at something like this and say, well, how did he come up with this? And sure enough, when you write the program and run it, it gives you a very good approximation of pi. Okay, well, let me run my program. Pi recipes, run as local application. Okay, so here is Ramanujan 0, and so this is a very nice approximation of pi. Now, of course, a double gives you about 16 digits, and so the last few digits may be off because of round off errors, okay? Now, formula number 2 requires that you have a loop. Okay, so here's formula number 2, and of course I explained that this sigma symbol is the mathematical way of specifying a loop where n goes from 0 theoretically to infinity, and you keep calculating these terms, and the sigma says add them all up, okay, and then of course you have to multiply by 1 divided by 882. Okay. And that gives you 4 over pi. And so if you want pi, you have to take the inverse of that and divide by 4. Okay. Now, the curious thing is, what is this minus 1 to the nth power? Okay. Okay. Well, whenever n is odd, this factor will equal minus 1. So for example, here's minus 1 to the 3rd power, and it's minus 1, minus 1, minus 1. You know? Now, minus 1 times minus 1 gives you 1 times minus 1 will give you minus 1, okay? Now, if n is even, then this factor gives you positive 1. So here is minus 1 to the 4th power. Now, every pair of them, minus 1 times minus 1 is 1. So this is 1 times 1, which is this positive 1, okay? So why do we have this? Why do we want this factor here that's, equal to minus 1 whenever n is odd and equals positive 1 whenever n is even? Well, basically, you want this whole term to be either positive or negative. In other words, sometimes you're adding and, well, every other value of n, you're either adding or subtracting. Okay, so that's why you have this weird factor. And this is the sort of the mathematical way of saying that you alternate between adding and subtracting, okay? Now, when you write the program, sure, you can use the PAL function and say -1 comma n, and you will get either -1 or +1, depending on whether n is 0 or is odd or even, okay? But as you see in my code, since I know what this is trying to do, you know, either you're adding or subtracting, I'm going to use a Boolean variable instead that's either true or false. Okay, I'm going to flip it back and forth between true and false. If it's true, I add. If it's false, I subtract. Okay, and that is a lot more efficient than calling the PAL function, especially if this number is very large. It's just going to, you know, do a lot of multiplications and who knows what kinds of round off errors you might get, because the PAL function is probably done with logarithms. And so if you know what this -1 to the nth power term is actually doing, you can write better code. Okay, so I have this warning here, which I had mentioned earlier, that if you just pull a formula like this straight out of a book or off the web and you code it directly into C++, and then you put it in a loop, well, if you don't do it correctly, you may accumulate round off errors, and pretty soon your answer will be way off, okay? I have this link down here, which you can barely see. It's actually a book that I wrote nearly 20 years ago, back when I was a lot smarter, okay? Let me show you the book. If you're interested in this sort of thing, numerical calculations and scientific programming. Okay. So this is a book that I wrote quite a while ago. And now all the code is in Java, but you know, Java and C++ are not that different, and certainly the arithmetic expressions are pretty much the same. But in this book, I talk a lot about how to do these calculations in a program and minimize round off errors and make the code as efficient as possible, and so forth. Okay, so if you're interested in that topic, at one time I was pretty good at that subject, but when was this book published? I think in 2002 or something like that. So let's see. I can't find the publication date. Oh, there it is. November 8, 2002. So it was nearly 18 years ago. And of course, I started writing it a couple of years before it was published. And so something I did 20 years ago. Okay. All right. Any questions? Okay. Oh, and I was going to show you the program that I wrote. So this Ramanujan number, this is number 0, and then number 2. Okay, so here's number 2, and you can see that I have this Boolean variable negate, and it starts out false, and if I'm supposed to negate, then the factor, okay, this factor that I compute, I will then negate it, okay? And if it's, if negate is true, then I will negate the factor, and if it's false, I won't. But at the bottom of the loop, you can see I say negate equals not negate, which then flips it. So if it was true, it becomes false, and if it was false, it becomes true. So each time through the loop, it's either true or false, and I'm either negating or not negating that first factor. Okay. So I think the code is a pretty straightforward. Okay,
Professor,
there's yes.
so would the result be different if your starting condition was true instead of false?
Oh yeah, then you would be adding when you're supposed to be subtracting and subtracting when you should be adding, and yeah, you'll get a very different result. Yeah, in fact, why don't we try it and see what happens? You know, I have a little soapbox speech that I always give, in that okay, we're talking about computer science or data science or whatever, and science means you do experiments. And if you wonder, gosh, what would happen if I did this? Well, not hard to do to change your program. Okay, so this, okay, I'm sure this will really screw up the first one. Okay, yeah, okay, so did it screw it up? Okay. Maybe we lucked out and it did. Oh, that's this recipe number 2. Oh, yeah, see, it came out to be a negative number. Okay, so we're lucky that all it did was flip the sign of the result. Now, sometimes you'll get a totally bizarre result, but yeah, it really depends on the formula. And okay, now we're back. Okay, so the way these formulas work is that each iteration gets you closer and closer and closer to pi. And now, given that doubles your limit to 16 digits, you can only get so close. And how do you know when to stop? Okay, well, you want to stop when 2 successive values are so small that it doesn't even show up in the print. Now, because we are dealing with doubles, and doubles you can get up to 16 digits of precision, I say that, well, all right, if the difference between the 2 numbers is less than 10 to the minus 17, then you may as well stop, because any further iterations will not improve the estimate. In fact, if you continue iterating, you may start getting further away from pi, because you're accumulating round-off errors. Okay. So now, whenever you do iterations that say that, okay, this number is supposed to converge, well, sometimes if you make a mistake, the number doesn't converge, and you'll have an infinite loop. So I always say, put a hard limit on the number of iterations, and I set 20 here. And so we stop iterating when we get 2 values that are so close that they're less than the tolerance, or we stop when we've exceeded the maximum number of iterations. Okay. If you screw up the formula and it never converges, your code may you'll have an infinite loop. Okay, and you don't want that. Okay. All right, so that was Ramanujan 2, and then the let's see, was there anything interesting about the code? Okay, let me, because I try to highlight in red anything that looked interesting. Okay, well, here, of course, I'm flipping the gate from true to false and then false to true. Okay, and of course, here, this is interesting.
Hello, Professor.
Yeah, question?
Yeah, I have a doubt.
Uh-huh.
In the question, it's mentioned that the difference between 2 consecutive pi values, if it's less than 10 power minus 17, then we have to stop iterations, right?
Right. So that's what you're seeing here.
Yeah, but the actual difference, what I can see in the code, it's the difference between like the inverted values 1 by pi.
Yeah. Okay.
That's
So
my doubt.
yeah. So here, this formula is actually giving you 4 over pi, and so if you're going to print out pi, okay, let's see. Then you have to. Okay. So we calculate 4 over pi, and then at the end, to print out pi, you take 4 divided by 4 over pi, which then will give you pi. And let's see, the difference here. Okay, I'm actually looking at the difference between 2 successive calculations of 4 over pi. Okay, so that's what I'm doing here. And then if the difference, as long as the difference is greater than the tolerance, meaning that the difference hasn't gotten small enough, I keep on looping. And of course, n is less than a maximum number of iterations. Okay. So now the thing I wanted to point out is plus equals. Okay. Now, does everybody know what that means? What does it mean to say sum plus equals factor 1 times factor 2? Okay, so what we're doing here is adding up. Okay, this is factor 1 and this is factor 2, and we're multiplying them together and we're adding them all up and storing that into sum. Okay, now sum must have started out as I must have initialized the 0 somewhere. Yeah, there it is. So sum starts out being 0. Okay. Now this plus equals, you're going to see that a lot in C++ programs. It's kind of a shorthand. Okay. This is really shorthand for sum equals sum plus factor 1 times factor 2. Okay. So let me write that down. Okay. This is equal to sum equals previous value of sum plus factor 1 times factor 2. Okay. All right, so the general rule of thumb is that whenever you, okay, let me put that here. Okay, whenever you see an expression like this, where you take the current value of some variable and you add something to it and make that the new value of that same variable, okay, you can say plus equals, okay? And there's minus equals and star equals and whatever. So here we're adding, and so it's plus equals, okay? Hopefully the first few chapters of the textbook has explained all this. I haven't looked at the book recently, so I don't remember if it has been explained. Okay, but C++ has a number of these shorthand type operators. Okay, all right. So that was the only really interesting thing about the that program. Now let's take a look at the Chetnovsky. Chetnovsky, as I wrote in the assignment, they are 2 brothers, and they're in their late 60s, early 70s now, and they, like Ramanujan, were very clever at coming up with these formulas for calculating pi. And so this formula calculates 1 over pi, and so after you've done the calculations, you take the reciprocal and you'll have pi. Okay? Now, once again, I warn you about copying formulas right out of a book. Here we see 1/2, 1 divided by 2. And so if you put that directly into your program, 1 divided by 2, where 1 and 2 are both integers, the result will be 0. Okay, and so instead of raising to the n plus 1/2 power, you'll just end up raising to the nth power, and most likely would have gotten the wrong result. Okay, all right. So here again is a fairly straightforward translation. Notice that what I actually did was, instead of cubing this number and then raising it to the n plus 1/2 power, I actually raised it to the 3n plus 1/2 power, because I just multiplied it out. So little things like that I did, okay? And all right, so to get pi, you have to take, okay, so this calculates 1 over pi, okay? So here's 12 times sum, there's the 12. And when you print it out, you want to print 1 over pi, which will then just give you pi again, okay? All right, and the result of that gives us these values. Notice that these formulas converge fairly rapidly. And so, you know, these two only took 4 iterations. This one took 3 iterations. Okay. Now, of course, if you wanted many more digits, and you really can't do that with a double, of course, then it will take more iterations to give you more digits. But since we're limited to 16 digits, it doesn't take very many iterations. Okay. And then the Machin formula. Okay, this is one of the earliest formulas for calculating pi, and it required that you have a arctangent function, okay? And so this is pretty amazing. No, I don't know why this came out in regular and this came out in italics. I was using a formula package to create these formulas. Yeah, but anyway, pi over 4 is 4 times arctangent of 1 over 5 minus arctangent of 1 over 239. And of course, again, you don't want to copy these formulas right out of the book because you otherwise would be doing integer arithmetic. But I gave you the formula for pi, and you had to write the arctangent function. So here it is. Okay. And notice that, okay, instead of writing 1 divided by 5, I said 0.2. And then here, to get this value, I made sure that at least one of the division operands was a double. Okay, and so here, okay, we have 1.0, and just for good measure, I made 239 also a 0.0. Okay. All right. Well, this gives us okay. This is the pi formula. Makes 2 calls to arctangent. Okay, arctangent. Now, C++ does have a built-in arctangent function. Okay, but hey, that's no fun using it. Let's write our own, and this is the formula for calculating arctangent. Okay, now this goes forever. Okay, but as you can imagine, as the denominator gets bigger and bigger and bigger, pretty soon the fraction will get so small that it will no longer make any contributions to the sum. And if you're iterating, that's when you need to stop. Okay, so this is a clever formula for calculating the arctangent of x. Okay, and that was the function I wanted you to write. Okay, so here, let's see. All right, here's the beginning of it, and now notice that whenever the denominator, well, first of all, the exponent and the denominator are the same value. Okay, and that it's always odd numbers. Okay, 3, 3, 5, 7, etc. And we alternate. Okay, first we subtract, then we add, then we subtract, then we add. Okay, so okay, let's see what I did here. Okay, I started out by calculating x squared. Okay, that's because this is x squared times x, this is x squared times x to the third, and so forth. And so I wanted to go ahead and calculate x squared. Okay, and each time through the loop, the numerator is multiplied by x squared. Okay, so we start out with x, and then multiply that by x squared, and we get x to the third, multiply that by x squared, and we get x to the fifth, and so forth. Okay, so I've got the numerators set up, and then the denominators are just the odd numbers. Okay, so we start out with odd equals 3. Okay, and then each time we add 2 to odd, and that gives us the next odd number. Okay. All right, now this fraction is easy. It's just a division. Well, the numerator, okay, is the x to the odd power, and the denominator is this odd number. Okay, and each time through the loop, we add 2 to the odd number to get the next one. Okay, and the same applies. We keep looping as the term is greater than the tolerance, and we make sure that we don't we have a hard limit on the number of iterations. Okay, and this returns whatever we calculate for the arctangent, which of course is here, and we're either adding a term or subtracting a term depending on the value of add sub, which is a Boolean, starts out false, and at the bottom of each loop, we then negate add sub so that if it was false in the previous loop, it's going to be true this time. Okay, so depending on whether add sum is true or false, we're either adding or subtracting the term. We're either adding the term to arctan or we're subtracting it from arctan. And arctan is the computed arctangent. Okay. All right, so once we have the arctangent function, then as I said, the pi formula is actually pretty simple. Okay, and if we look at the estimate, okay, well, we got most of the digits, not all. Okay, whenever you have a yes.
Would it be okay to use the generic formula for the arctan, which is -1 to the power n, and that one, x to the power 2n plus 1 upon 2n
Well, as I said, there is a built-in arctangent function, and you are welcome to try it to see if you get the same answer. But I wanted you to write this function, to get practice doing this sort of thing. Okay, what was that your question?
No, I mean, with the generic formula, if we do the summations and do it the same way, except with because that does add on to the same thing, right? I mean, it would compute the same, right? So summation of that.
Okay, well, okay, I'm not sure I'm understanding your question, but okay, the summation is happening here. Okay, arc10 starts out being x, right? Because
Professor?
Yeah.
I think she's asking if we can use the Taylor series representation of arctangent and implement it like that.
Oh, isn't this the Taylor series?
Well, like in the summation version, like similar
The
to
summation of series, the formula for the summation of the series.
Okay. Well, I would say that you should code it up the way I have it here. And if you want to try a different summation formula, then sure, and, add it to the assignment and see how the answers compare. Yeah, so you can always do more than I ask, and as I said, with computer science or data science or whatever science, it's all about trying out different things and doing experiments. Okay, all right. So does that answer the question? Okay. All right. Well, speaking of predefined functions, okay. Oh, and let's see, did I post these? Well, of course, the solutions in the slides, but I will post my program so you can play with it. Okay.
Professor, I have two questions.
Yeah.
One is this assignment gonna be graded on efficiency? What if you use the power function, built-in function instead of using the Boolean?
No, we're not grading on efficiency.
Okay.
Just as long as we see that you have, written arithmetic expressions in C++, and your numbers are close. Okay.
Okay.
Depending on how you coded these things, the last 2 digits may be off. Now, I was just looking at this and seeing that, okay, here I've got integer values. Now, we're not doing division here, so that's okay. But what if I had made these doubles? Would that have changed the final answer? And well, that is an example of an experiment that you can do. Okay, it's very easy to do these sorts of experiments. Okay.
Okay.
All right. Yeah.
My second question was when will we see our assignment grades?
Okay. Here's the thing. I have a ISA that I want to hire for this class, and I think she hasn't started yet because the computer engineering department is still trying to figure out what its budget is going to be for the ISAs, and therefore we don't know how many hours they can work. But hopefully within the next few days, they will have a budget, and then she could start working. In the past, okay, I've taught this class several times. In the past, I've actually had enough in the budget for the ISA to also provide tutoring. Okay, now back in the old days when we were able to actually go on campus, during the week, the ISA would have office hours, and we had an office set up for it's actually a shared office set up for the ISA. And if you had any questions about the homework or whatever, you can go and meet with the ISA, and then he or she will be able to give you some tips on how to solve the homework problems. Okay, now that we are no longer on campus, and we have evidently a budget crunch, I suspect I'm not going to get approval for the ISA to also be have office hours. So we'll see how it goes. But hopefully we'll get the ISA situation resolved within the next few days.
Sounds good. Thank you.
Yeah, she was. I know which of my ISAs are women and which are guys, but I don't remember which one got assigned to which class. But the ISA that I'm thinking of also was a grader for me last spring. So she knows what I expect. All right, but then I'm not necessarily giving you the same assignments. And so there'll be some new assignments and then some older ones. Okay. All right. Any more questions about?
Professor, I had one. So this is not related to the assignment. It's actually about code check. So when we do submit it, it says either a 0 of 1 or 1 of 1. I just wanted to know what exactly that means.
Oh, okay. Well, if I give you an assignment where the answer is exact, then it will say, okay, 1 over 1, okay, meaning that you got a perfect score, okay? Now, some assignments, we cannot get exact values, and so it's unlikely that you'll be able to match my answer. So it's actually comparing your program against my program. And, for some assignments, there's no way to guarantee any sort of match. So CodeCheck says, well, if there's anything that doesn't match, it's a 0 over 1. But as I said, for this assignment, don't worry about that because you know, we're not going to be able to get exact matches just due to the different ways that we write these expressions. Okay, so that's code check. Oh, and the practice problems. Okay, so in the past, every week besides the main assignment, there would be 4 short practice problems, each worth 5 points, and it's, you know, to give you some practice with a specific feature of the language, and you may want to use that feature for the main assignment, so it's good to have a little bit of practice. Now, you would access those practice problems through Canvas, just like you access the main assignment, but Canvas will then take you to a version of CodeCheck, okay, so that when you do the practice problems, CodeCheck will automatically grade them and assign the points. Okay, I said I think there'd be 4 practice problems and each worth 5 points, so you could get a maximum of 20 points. Okay? So this requires some integration between Canvas and CodeCheck. In fact, with the practice problems, not only will CodeCheck automatically grade them and assign a score, but it will then enter the scores back into Canvas. So, you know, no ISA needs to even touch this. This is all automated. Okay. Well, it broke over the summer, this wonderful tool, and I may be able to get it back up maybe sometime this week, and then I'll be able to start assigning practice problems again. Okay. So that's the story behind the practice problems. Now, there were a few instances where students would tell me that it took longer to solve the practice problem than it did to solve the main assignment. Now, I don't know if I could really believe that, but I've been told that several times. So practice problems were supposed to be short and easy, but I guess maybe not always. Okay. All right, that was assignment 1. And I hope to be able to go over each of the assignments at the beginning of the class. Some of you noticed that I accidentally posted the solutions, I think last night. And so some of you may have seen my solution, but as long as yours is different from mine, that's okay. All right, so predefined functions like square root and log, they come with C++. So if you install C++, you get these built-in functions, although you do have to say include CMath, okay? And that's where most of these built-in functions are defined, okay? And I have a little table here that I stole from the Savage textbook. And you can see there are a small number of functions shown here. There are probably dozens and dozens of these. And so if you Google CMath, it'll probably have a list of all the functions, okay? And I mentioned include CMath, but also you have to say using namespace std, okay? Otherwise, the compiler will complain that it doesn't know what sqrt is, okay? All right, now I want to talk about random numbers because your next assignment is going to use random numbers, okay? Now, when we talk about random numbers with a computer, you're not actually getting true random numbers, you're getting pseudo-random numbers. And they're pseudo-random because even though they look random, they're being generated by an algorithm. And so, you know, if you run these algorithms long enough, you'll start detecting patterns in the random numbers because they're generated by an algorithm. But for most intents and purposes, the random number functions are good enough, okay? All right, so if you're going to write a program that uses the built-in random number functions, you have to also include these two header files, CST lib. It looks like this is C standard library, and this is C time. Okay, and you'll see why we need to include the time libraries. Okay, all right. So then you want to seed the random number generator. Now, remember, these pseudo random numbers are being generated by a formula. Okay, and you want to seed the generator by giving it an initial number, okay, and then each random number, it applies its algorithm to generate the next random number, okay, but it has to start somewhere, so you give it a seed, okay. Now, if you run your program with the same seed, then you'll get the same sequence of pseudo-random numbers, okay. So if you want to make it a little bit more realistic so that every time you run your program, you get a different set of random numbers, then you have to give it a different seed every time. And a very common way of doing it is to use the current time as the seed, okay? And so then every time you run your program, it'll be a different current time, and therefore you're giving your program a different seed, okay? Now, why would you want to give it the same seed every time, and therefore your program gets the same sequence of random numbers? Well, let's say your program has a bug, and you run your program, and then something bad happens, and you're trying to track down what that bug is, okay? Well, then you want to have the same sequence of random numbers so that you're guaranteed that bug will occur, okay? Because often you'll have bugs that sometimes happens and sometimes doesn't happen, and those kinds of bugs are really hard to debug because it doesn't always happen, okay? So if your program, which uses a pseudo-random number sequence, maybe has a bug, then you want to make sure that every time you run that program, because you're doing debugging, you get the same sequence of random numbers so that your program behaves the same way every time, okay? So there, SRAN, you would just give it the same number. It could be 12, it could be 3, it could be 0, whatever, and you'll get the same sequence of random numbers, okay? Now here, I'm giving it seed the current time so that every time I run the program, because it'll be a different time, we'll get a different sequence of pseudo-random numbers, okay? Now, what exactly is this time, okay? Well, the story is that the folks who first developed Unix, okay, they wanted to record the time. And so they said, okay, we'll record the number of milliseconds since January 1st, 1970, probably midnight, January 1st, 1970, and that will be 0. And then we'll keep track of how many, I think it's milliseconds since that time, okay? So inside your computer is this counter that's counting up, by milliseconds, and that is the current time, is the number of milliseconds since January 1st, midnight, 1970, okay? And so that's what this is giving us, okay? It is a long integer, is the number of milliseconds. Okay? Now, some of you may remember the Y2K problem that we had, well, I guess 20 years ago, when a lot of programs stored the year with only 2 digits, only the last 2 digits of the year, so that when it turned over from 1999 to the year 2000, a lot of computer programs would think it's the year 1900, Okay, so that was the big Y2K problem, the year 2000 problem, and people had to go in there and rewrite their programs to store more than 2 digits for the year. Okay, now there's a similar problem about to occur here. This is the number of milliseconds since January 1st, 1970, and the storage that was allocated for that number, well, it's about to run out. You know, it's going to turn over to 999999999 and then become 0 the next millisecond. And so we have our own version of the Y2K problem, but I believe they're working on it, and they probably doubled the size of that storage. And so it may be a million years before we run out of milliseconds, at which time we will no longer have computers the way we have them today. Okay. All right. So random numbers. Okay. And when you call rand, okay, so after you've seeded the random number generator, this srand or seed rand, every time you call rand, it will return to you the next random number. Okay, it'll return a random number to you, and that random number will be greater than or equal to 0, but less than or equal to a value named rand max. And rand max is library dependent, depends on what C++ library you're using, but it's guaranteed to be at least 32,767. Okay, so every time you call rand, you'll get a number greater than or equal to 0 and less than or equal to this system constant rand max. Okay, now quite often you want random numbers within a certain range. So maybe you're simulating some sort of dice game, and you want a random number to represent somebody tossing a die. Well, die values are 1, 2, 3, 4, 5, or 6, and so you want random numbers that's only chosen from those 6 numbers. And so here, for example, okay, you take the modulo of the random number, and that's whatever is left over after you divide it by 6. And so now, this expression here, the call to the random number function, modulo 6, will give you random numbers 0, 1, 2, 3, 4, or 5. And if you really, really want it 1 through 6, then you have to add 1. And then now you have random numbers made up of just those 6 digits. Okay. I'm telling, yeah.
How would you include 0 in that?
Well, then don't add 1. Okay, then you'll get 0 through 5. And if you want 0 through 6, then you take modulo 7. Okay.
Okay.
Okay, now I'm telling you all this because your next assignment will involve random numbers, which I'll talk about your next assignment at the end of our class. Okay. All right. Typecasting. Okay, and again, when you did assignment number 1, and you know, some of you ran into problems between integer and double. Well, there's a feature called typecasting, and okay, I've already gone over this. You have 2 integer variables, I and j. They have values 5 and 2, and what's the value of the division I divided by j? Well, I and j are both integer, and so therefore we only get back an integer result, and so we'll get 2 as the result. Okay. Now, what if you really, really needed a quotient of type double, but all you have are these 2 integer variables, okay? And you want the same fraction, okay? But you want the result to be a double, not a truncated integer, okay? So there is this way of doing it. Now remember, for division, if one or both, okay, either the numerator or the denominator, or both of them, if one or both of the operands of the divide is a double, then the result of the division will be double, okay? And now if all you have are I and j, then here's one way to do it, okay? You call this function called static cast, okay? And in angle brackets, you say, well, what data type do we want to convert to? And in parentheses is the value that you want to convert. Okay, so what this says is that we're going to take the value of I and whatever it is and make that value a double, okay? And then we divide that by j, but now the numerator is a double value, and so when we do this division, we will get the fraction, okay? So static cast is the way we do casting, okay? Okay. Now, what about this second statement? Okay, I'm going to say right off the bat, this one will not work, and why not? Okay, well, let's see what's happening here. We do the division, and then we say, okay, we want to cast that to a double value, and will we get the same answer as what we had up here? Okay.
No.
What do you think? Yes or no?
No.
No.
No, and why not?
Because we're doing the division first
It's an
instead of.
That's
Yes.
an expression.
Okay, so before we apply the cast, we have to do this division, and both I and j are integer, and so we'll get an integer result. Let's say we get 2, and then we're casting that to double, and so quotient will have 2.0, okay? And that may not be what you want, okay? So be very careful how you do these sorts of arithmetic operations, okay? Okay, now, of course, besides the built-in functions, you, the programmer, can write your own functions, okay? And those are the programmer-defined functions, okay? And I'm going to say that having those programmer-defined functions will make your code a lot easier to read, because you break things up into smaller pieces, and by good use of names for your own functions, you can make your program very easy to read, okay? Now, what I'm saying here is that before your program can actually use a programmer-defined function, you must have either declared or defined the function. Okay, so let's go back to my example of, okay. All right, so all the way up here. Okay, this function, Chetnovsky, okay? Well, how am I allowed to call that function, okay? Well, even though the function is defined later in the code, because it's way down here, okay, I had previously declared it, okay? So if we go up to the top here, we should see the declaration of Chetnovsky, okay? Now, that means that when I actually use Chetnovsky in the program, okay, it's here. Okay, so here I am calling the Chetnovsky function, okay? The compiler will know what this is because it previously had already seen the declaration. So it knows that Chudnovsky is a function. Okay. Now, okay, so that's what this paragraph is saying, is that before you can use a program, a function, it must have been already declared or defined. Okay, so here, here's what we could have done. Okay, instead of having that declaration up there, okay, we could have just put the function up at the top. Okay, okay, let me remove it from there, and then instead of this, we actually have the function. Okay, that works too, because as long as whoever calls the function has seen either the definition or the declaration of the function. Okay. All right, so well, let me run this to make sure. Okay, the program is still happy. Okay. All right, let me put it back where it was. Otherwise, the next time I teach using these slides, I'll get very confused. Okay. All right, so you could write your own functions, and I kind of gave you a little bit of practice by writing these pi formula functions. Okay, so you had to write, the code that goes into each of these functions. Okay, and of course it was the main that called the function. So here, whoops. Okay, so here's the main, and it says, okay, here's the Ramanujan pi formula, and then it calls Ramanujan, okay, which will end up printing the value, and then there are the other Ramanujans and Chudnovskys, and there's actually one more program way down here, if I can find it. No, okay, I guess that's it then there, because here's the Mackin formula, okay. Okay, so after either having seen
One question.
yeah.
Yeah, we are declaring a function twice here, one at the top and one below the main function. So when we call the function, it goes to the function that we have declared below, doesn't go to the top one.
Well, the top, there's no code here. It's just a declaration, so that when you call the function, you had better define the function with the actual code. Okay, so so the computer will never go to one of these, because it's only the declaration of the function. It's not the function itself.
Okay, thank you.
So so don't worry about that. It's very interesting, the questions that students ask. It's like, oh, I never thought of that. Or, oh, I never realized that could be confusing. And so it's always good for me to hear questions, because I always learn what is it that's confusing students, and I need to explain better. Okay. All right, so a function declaration specifies the name of the function, the number, order, and data types of its formal parameters. Now, here in my declarations here, okay, we obviously get the name of the function, okay, we get the number, order, and data types of its parameters. Okay, well, here there's only one parameter, but its data type is int. Okay, and what is the return value of the function? And so here in this case, after we've calculated the factorial, we're going to return it as a double. Okay, so each function declaration does say a lot. Okay, because when we start looking at the main, and the main is calling these functions, it hasn't seen the definitions yet. It's only seen the declarations, but the declarations have enough information in them that the compiler can go ahead and generate the code to call the function. Okay, so it's going to generate code to call Ramanujan 1 and 2 and so forth. Okay. Okay. Any questions about what a declaration is? Okay. So a declaration basically says, okay, name of the function, return type, what parameters, and how many of them, and in what order do they come. Well, here we only have one parameter, so there it is. Okay, so that's the declaration. And then, of course, you saw earlier that once you've declared the function, you had better define it. Otherwise, the C++ linker will become unhappy with you. Okay, and here are, here's an example of, okay, so total cost
Excuse
is,
me,
yeah,
Professor.
Go ahead.
I had a question. I had a question about the declaration.
Yeah.
In assignment number one, Ramanujan number 1 is defined after Ramanujan number 0. Both the function and the pre-declarations are after the Ramanujan number 0. Can we use the function number 0 inside number 1? Can we use Raman number 0 inside
the functions can call each other.
1?
Yeah, so the function can call each other. Now, it may not make sense for this assignment, but Ramanujan 1 can contain a function called a Ramanujan 0. Okay, so yes, functions can call each other. Okay.
Yeah.
All right.
Yeah, thank you. That answered
Okay.
my question. Thank you so much.
Okay. You're welcome. All right. So now the definitions, of course, fills in the actual code. Okay. So after you've declared the function, we're declaring total cost. Later on, you have to give the definition of total cost. Okay. Otherwise, it'll be an error if you declared a function and then you never define it. Okay. All right. Now, if the function is supposed to return a value, you would specify, well, what data type. Okay. So here, total cost is going to return a double value, and somewhere in your function, you need to say, okay, I'm returning, and I'm going to be returning some local variable. Okay, and so you can see here that total, the variable, is type double, and when we return total, it's going to match the data type of the return, the variable you're returning matches the data type of the function. Okay, so any code that calls total cost is going to get back a double value. Okay. All right. So okay. Well, how do you call a function that you wrote? Well, you call it the same way as you would call a built-in function. Just name it, and in parentheses, whatever arguments you need to pass to that function. Okay. All right.
I have a question.
Yeah.
If I do not use the built-in function, should I still write the include namespace at the beginning?
Oh, yeah. If you do not use the function, then you do not have to do the include.
I mean, I don't use the inbuilt function, but I'm going to calling the function I define by myself. Should I still?
Yeah. at the top of your program where you specify these includes, okay, so here I'm including CMath, and I'm including it because I know I'm going to be using the built-in math functions like square root and logarithm and so forth, okay? Now, if my program does not use any of the math functions, then I could leave off the, so I have this here only because I am using built-in functions from the library, okay? So
but the part use namespace standard should always be there.
Yeah, you should always put this here because I think string is actually a name that's in the standard namespace, and if you leave off using standard namespace, you can't even say string. You'll get an error. Okay. All right. So here's how we call a function. You just call it the same way you would call a built-in function. Okay. And now there's something known as a void function. Okay. Now the functions that we have here, this is a double function. In fact, oh, here's a void function. Okay. A void function does not return a value. It just returns. Okay. So here we have a void function called printf, and you can see that we're passing in a Boolean value, and if the Boolean value is true, we write out T, otherwise we write out an F, okay? So this function is not calculating a value, it's given a value, and it's not using it. Well, it uses the value that is given, but it's a void function, and so it's not going to return a value, okay? And you can see here, we actually don't even have a return statement, because when the computer is done executing this if statement, it's going to return automatically. So we don't need to put a return statement here, okay? Now for a function that does have a value, then you will need a return statement so that the computer knows what value are you returning as the value of the function, okay? All right.
Professor?
Yeah.
Why the main function is integer function instead of the void function?
Okay, Here's an good question, okay? Notice that at the bottom here, I return 0, okay? And therefore, main, which is actually just another function. It just has this special name. Why is it int and not void, okay? When you run a program from the command line, okay, in a terminal window, you can actually return a value. So that, okay, let's say that on the command line, I run my Py program, and the Py program will end up returning 0, okay? Now, why would you want to return a value, okay? Well, it could be an error code that you return. It could be any integer value, okay, that you can return. Now then the question is, who gets that value, okay? Well, if you're on the terminal's command line, you could run your program and have the return value automatically assigned into a variable, okay? So the bottom line is that if you're running your programs from the command line, okay, the programs can return a value that, using various operating system tools and whatnot, you'll be able to get a hold of that value that the main program is returning, okay? Okay, so any other questions? Okay, these are all good questions, but okay, so void function does not return a value, okay? And now it's a void function. That means it doesn't return a value. Therefore, it makes no sense to make a void function call as part of an expression, okay? Because it doesn't return a value. And so only functions that return a value are you allowed to use it in an expression. Okay, so here, if we look back at, I guess not number 0, okay? All right, you see all these calls to square root, okay? Now, square root is a function that returns a value, and so we can put calls to square root inside of expressions, and it makes sense, okay? This will be 12 divided by the square root of 190, okay? But let's see. Main, okay. Okay, well, Ramanujan 0, okay, it does not return a value. So when you call a void function, it has to be called as a statement. Okay, so let's take a look at Ramanujan. Okay, so here I'm calling, okay, and let's see, Ramanujan, okay, hang on. Okay, right, 0, 1. Okay, these are all void functions, okay? So I cannot put the function calls in a formula, okay? But I can call them as separate standalone programs. As you can see here, Ramanujan 0 is being called. This is an example statement. It's not part of an expression, okay? All right, so that is how we call void functions. The call is just another type of statement, okay? Not part of an expression, okay? Okay. Now, I already mentioned the coding conventions. We declare the functions before the main, and then we define the functions after the main, okay? That's just a coding convention. There's no rule that says you have to do it that way. Although you should know that if you have a function call in your program, that the C++ compiler has to know what the function is. Okay, so either by the time you call a function, okay, you must have already seen the function declaration or the function definition. Okay, but if you try to call a function that you've not seen yet, okay, there was no declaration at the top, and there wasn't definition right after dinner, and here it is late at night, and so okay, so you have to then make sure that you have either declared the function or you have defined it before you actually call it, okay? All right, so then make sure that when it's getting late at night and you're coding, that you don't make that mistake of trying to call a function that the compiler hadn't seen yet, okay? The compiler just reads your program from top to bottom, and it has to have seen either a declaration or a definition before you can actually call the function. So that's what I was trying to say, okay? All right, and here again is an example. Here's the main, and before the main, we have a couple of function declarations. Okay, here's an integer function, here's a void function, and then after the main, we actually write the code, okay? And here we have comments that say what the function does, okay? And here we see the @param and @return, okay? And down here, where we actually write the code, we do not repeat the comment, but we can have an internal comment, okay, that's explaining internally what the function is doing. Okay. And here we can call make sum and print because by the time the compiler is compiling the main, it has already seen make sum and print. Okay. All right. Okay, let's take a break. And after the break, I'm going to show you an example of how to write not a real complicated program, but a non-trivial program in a top-down fashion. Okay, quite often students have a hard time understanding how to go about starting to write a program or how to design a program, and I'm going to show you one way to go about doing it. Okay, so we'll do that after the break. And how about we break until 7:45 or so? Okay, how about that? Okay. All right, and at 7:45 we'll come back, and as I said, we'll learn about top-down design. Okay. All right. Okay, is everybody back? All right, so I was going to spend some time giving you a demonstration of what's known as top-down design. It's a very important software engineering principle. Okay, so how does top-down design work? Okay, well, you start with the topmost subproblem of a programming problem. Okay, so you write a function for solving the topmost subproblem, and then you start breaking each subproblem into smaller subproblems, and you write a function to solve each subproblem. Okay, and this whole process is known as stepwise refinement, because each step you incrementally refine your solution. Okay, now here is, okay, so when you do top-down design, you end up with this hierarchical decomposition of the problem, also known as a functional decomposition. Okay, it's basically you take a complicated problem and you break it up into these hierarchical parts, and you work your way down from the top. Okay. Okay, so here's an example. We're going to write a program that inputs from the user numbers that are positive, okay, integer values less than 1,000, and we're going to translate that value into words. Okay, so that may sound like it's not a trivial problem. Okay, so for example, the user enters the digits, 482, and your program writes out 482, and you keep doing this until the user enters a value that's less than or equal to 0, and that tells the program that it's done. Okay, so that's the problem we're going to solve. Okay. All right, well, let's see how we go about doing this using top-down design. Okay, well, so what is the topmost problem? Okay, the most basic problem. Well, it's to read in a number from the user and keep asking for more numbers until the user types in a number that's less than or equal to 0, and then we're going to translate each number into words. Okay, that's basically, in a nutshell, what the program is supposed to do. And so that's a high-level description. Okay, now here's the first version of the program. Okay, we're going to create a loop to read and print the numbers that the user is typing in. And then for each number, we're going to call the translate function. Okay, but since this is the first version, the translate function doesn't actually do anything. Okay, so this is translator 1. Okay, and I have posted these programs. Okay, so here is translator 1. Okay, there it is. Okay, and you can see that, okay, I have a declaration of a function called translate. Okay, and you can see it takes an integer value. Okay, and it's going to translate that integer value into a string of words. Okay, so here you see that it's going to return a string. Okay. Now here's the main. Okay. It has a loop. Okay. And what it does is that each time through the loop, it asks you for a number. Okay, so it's prompting the user for a number, and the user types in a number, and that number is then stored in variable number. And if the number is greater than 0, okay, because remember, we stop if the number is less than or equal to 0, we write out the number, okay, colon, and then we write out the translation of that number into words. Okay, and we keep doing this until as long as the numbers are greater than 0, and when we're done,
don't you also have to test that the numbers are less than 1,000?
Yeah, we should do that. Okay, so that's good. We should test to make sure the number is less than 1,000. But you know, we're starting out from the very beginning. But you're right. We probably should test to see if the number is less than 1,000. Since we said the problem is less than 1,000. Okay, so we should have tested that. Okay. All right, and then as soon as we get a number that is less than or equal to 0, we drop out of this loop and we write out done. Okay. Now, the translate function is the function that's going to translate the number into words. And so, see, we write out the result of calling the translate function. And remember, the result of the translate function is a string. And so we could write it out. Okay. But this is the first version. And so all we're going to do is write out or return a string of question marks. Okay. So this tests our input and tests whether or not we can read a number, write it out, whether or not we can call the translate function, even though it doesn't really do anything. And when we put in a number that's less than or equal to 0, it's supposed to end. Okay, so let's run this first version. Okay, and you know, we could have written this first version in 15, 20 minutes. Okay, so run as local C++ application, and there it's prompting me for a number. I can type in 1, 2, 3, and it says, okay, it's going to write out 123, and here is our initial translation, which of course is just question marks. Okay, I can put in 9, and there it goes. And as soon as I put in a 0, it will say, okay, we're done. Right? So if I were to write this number translation program, this would be my first version. Okay. Now I know I can read in the numbers. I know I can write out the numbers. I can call the translate function, and I know when to stop. Okay. All right. Well, now that we have this working version, let's see what version 2 will be. Okay. That's refinement 1, refinement 2. All right. So now let's start thinking about the translate function. Okay. How do we translate a number into words? Okay, well, we can break the number into separate digits, and so we can translate the digits into words like 1 or 2. Okay, and then here are other words. Okay, so we're going to refine the translate function to handle some simple cases. Okay, we can translate a ones digit from 1 through 9, and we'll also be able to translate teams 11 through 19. Okay, this will be our second version. Okay, so we're starting to break apart the translate function into smaller functions that will solve more of the problem. Okay, so here is translate 2. Okay, all right, well, we still have the loop. That hasn't changed. Here's the translate function. Okay, so what have we done to the translate function? Okay, well, if the number n is less than or equal to 9, then we call translate ones. Okay, so we're translating a ones digit. Okay, if the number is greater than or equal to 11 or less than 9 or equal to 19, then we call translate teams. Otherwise, we don't know what to do, so we just say words is equal to the 3 question marks again. Okay, so translate ones and translate teams, which we have declared up here. Okay, here is translate ones. Okay, it translates a ones digit into a word, and here's translate teams. It will translate a teens value into a word. Okay, so all right, well, let's take a look at what translate 1 does. Okay, well, we do a case or switch on the value of n, which we know is a single digit, right? Because when we call translate ones, we check to make sure that n is less than or equal to 9. And so depending on the value, we write out the appropriate, or we return the appropriate word. Okay, remember the function returns a string. Okay, now this should never happen, but you know, switch statements like to have a default, and so even so this default should never happen. Okay, but we haven't
Professor,
returned. Yes.
wouldn't it work if you entered in 10? It would go default, right?
Right. Well, okay, the number has to be less than or equal to 9, or from 11 through 19. And if we enter the 10, it's going to come down here, and we'll get the 3 question marks again. Okay, so, and then for translate teens, we know that n is from 11 through 9, and so so here we go. We do the same thing. Okay. All right. Well, let's see how much further we've gotten with version 2 of our program. And so now let's see. Okay. So well, yeah. If we enter a negative number, of course, then it will be caught out here, and that would end the program. Okay. So let's look at version 2 of the program. Okay. And now, if we give it a single digit, see, we've made some progress. We can do 12, and it knows about 12. It knows about 18. It doesn't know about 10. See, there it goes. And it doesn't know about any other number. Okay, so, okay. But we've made some progress. We can now translate single digit numbers and most of, well, and the teens numbers, okay, from 11 through 19, okay? All right, well, let's see what we can do with refinement number 3, okay? Okay, now let's see if we can tackle a 3-digit number, okay? And to do that, we're gonna separate out the hundredths digit, okay? And translate the hundredths digit, okay? Well, the hundredths digit is simply a ones digit translation followed by the word 100, okay? So that makes it easy to handle the hundredths digit, okay? Now let's see what else we can do. Well, how about if we're getting a 3-digit number, okay? And we can easily translate the ones digit, okay, just translate ones followed by the word 100. What about the last 2 digits, okay? Well, we already know how to handle teens, okay? And if it's not a teens number, then we can break it apart into 2 digits, okay? A tens digit and a ones digit, okay? Well, a tens digit would be translated to 10, 20, 30 through 90, and we already know how to translate a ones digit, okay? So again, we're given 3 digits, 3-digit number. We separate out the hundredths digit, okay? And translate hundredths, well, simply translate the single digit and tack on the word 100. So we get 100, 200, 300, and so forth. And then the remaining 2 digits, well, if it's a teens number, we already know how to do that, okay? Otherwise, we break apart the 2 digits, okay? There's the tens digit, which we can translate into 10, 20, 30, and so forth. And then the final ones digit, we already know how to translate, okay? So this is our 3rd version, okay? So I can handle up to 3-digit numbers, okay? Well, let's see how that one works. Okay, so this would be translate 3. Okay, let's take a look at the code, okay? So now we have translate tens, which we didn't have before, and translate hundredths. Okay, so we added 2 new functions. All right, so we call translate, okay? Now, translate can handle up to a 3-digit number, okay? Okay, now to get the hundredths digit, okay, we divide by 100. Now this is integer division, okay? N is an integer, 100 is an integer, and so this will throw away any fractional part of the division and will only get the hundredths digit, okay? So for example, if we have 123, okay, divide that by 100, okay, that's just going to give us 1, okay, which is the hundredths digit. If we give it 545 and divide that by 100, well, we'll get 5, okay? So this is a way of getting the hundredths digit, okay? And we're checking to make sure that when we do that, that the hundredths digit is not greater than 9, okay? So otherwise we get number too big, okay? All right, if we have a hundredths digit, it's greater than 0, okay? Then we say translate hundredths using that hundredths digit, okay? And let's see what translate hundredths does. Okay, translate hundredths, okay? All it does is takes that single digit called translate ones on it, which we already have, and tack on the word 100, okay? So there we go, okay? Now, after we've translated the hundredths digit, okay, we need to then look at the remaining 2 digits, okay? And to get the remaining 2 digits from a 3-digit number, we do a modulo of 100. Okay, now notice this is modulo equals, and so what we've done is that we've taken the value of n that was passed in, hopefully it's just a 3-digit number, and we divide it by 100, okay, but only keep the remainder. So if we passed in 523 and you divide it by 100 and keep the remainder, you get 23, okay? If you pass in 944 and you take the modulo of 100, okay, so divide 944 by 100 and just keep the remainder, you get 44, okay? So now n has been reduced to just the last 2 digits, okay? Well, we check, is n now a teens value? And if so, we certainly know how to translate teens, okay? Otherwise, we take the 2-digit number and get the leading digit, the tens digit, okay? Same trick we did up above. We divide by 10. So if the last 2 digits were 45 and we divide by 10, we'll get 4, okay? And then we do a translate tens on that digit. And if we look at translate tens, you see, okay, if the tens digit's a 1, then the translation is 10, or 20, 30, 40, 50, all the way up to 90, okay? And if it's 0, we return the empty string, okay? All right, so that's the tens digit, okay? And now we have to then, of that 2-digit number, we're going to get the second digit. And again, we use the modulo operator. So if n was 45 and we divide by 10 and keep the remainder, we get 5. If n was 97 and we divide by 10 and keep the remainder, we get 7. Okay, so this is how we get the ones digit. Okay, and if that ones digit is greater than 0, well, we know how to translate ones. Okay, now you may notice that as we're calling these translation functions and getting back the translation string, okay, we've been appending it to this string called words. Okay, words starts out being the empty string. Okay, and every time we call one of those functions, and okay, so here we're calling. Let's see, number too big. Oh, here we're calling translate hundreds. Okay, whatever string that translate hundreds returns, we're going to append it to words. So this is like saying words equals words plus translate hundreds. And then if you have strings and you're using the plus operator, you're concatenating them. Okay, so this is saying take the previous value of words and tack on whatever translate hundreds returns. Okay, and you see here, take whatever is in words and we're appending whatever translate teens returns, and same thing here with the tens and the ones. Okay, all right, well, now we can go up to 3-digit numbers and let's see what happens. This is refinement 3. Okay, so we did a couple of things here. Number one, we are now able to translate the hundredths digit, and then we're able to translate the remaining 2 digits of a 3-digit number. Okay, so let's see how that works. Okay, okay, so this is version 3, and let's run it and see what happens. Run as, whoops. Okay, how about 123? Okay, look at that, 123. Okay, I'm just making up numbers as I'm typing it in. 793, and if there's no hundredths digit, then we just get the translation of the last 2. Okay, so here's 84. Okay, now you see here that we call translate hundreds. Okay, translate. Okay. We call translate hundreds only if the hundredths digit was greater than 0. Okay, so that's why when we passed in a number that had no hundredths digit, it didn't call that function. Okay, and then when it comes to translating the last 2 digits, okay, okay, this. Okay, so we got 900, and then we got the last 2 digits. Okay, well, we pick off the tens digit, and that gave us the 20, and then of course the last digit is the 6. Okay, but let's do 905. Okay, well, now there is not a tens digit or a 0. Now remember when we did translate tens, where is it? Tens, if it was 0, we didn't return, we returned an empty string. So now we have 905. Okay, and we can also do 7. That should give us 714 because the last 2 digit happens to be one of the teens numbers. Okay, all right, so here we have the ability to do 3-digit numbers. Okay, now if you look back at the original problem, okay, you see that between a tens number and a tens word and a ones word, we really ought to have this hyphen here. Okay, that's the way we write out numbers. Okay, so let's see if we can figure out how to stick in that hyphen. Okay, so all right, so that would be, so we were looking at version 3. Version 4, we're gonna simply add the hyphen. So this is a minor refinement, but it's something that is necessary, that we're gonna stick in that hyphen. Okay, so let's see how we do that. Okay, all right, so that's number 4. All right, number 4 says, okay, oh, let me kill off this program. Okay, number 4. Now let's see, where should we stick in that hyphen? Okay, well, here's the translate. Okay, do the hundreds digit, do the teens digit, do the tens digit. Okay, and okay, after we've done the tens digit, okay, and if the tens digit is greater than 2, okay, right? Because it's only numbers like 20, 30, 40, 50, etc. that we have the hyphen. Then we insert the hyphen. So here we are inserting the hyphen between the word for the tens and the word for the ones, okay? Now, we do have some tests, okay? So after we've done the tens digit, we have to check to see if there is really a ones digit, because if it's 0, then of course we don't say 20 0 or anything like that. And so here we do the translate ones only if the remaining digit is greater than 0. And here, if it turns out that the tens digit was greater than 2, then we insert the hyphen, okay? All right, so we did it up at the we did that in the translate function, okay? It seemed like that was a reasonable place to put it because the translate function knows about tens words and ones words, and it can then stick in the hyphen if appropriate. Okay, so let's take a look at version 4. Whoops, that wasn't what I wanted to do. I wanted to say run as. Okay, there we go. Okay, 1, 2, 3. Oh, look at that. We got a nice hyphen in here. Okay, that did not require a hyphen. That doesn't require a hyphen. This doesn't require a hyphen. But if we do 952, that gives us the hyphen. Okay. And of course, as before, well, we can handle less than 3 digits. Here's 23. Here's 1, and there's 95. Okay. So now we're doing a pretty good job of translating these numbers, okay? All right, well, we've been limiting ourselves to 3-digit numbers. Let's get really ambitious and do up to 6-digit numbers, okay? Well, how are we gonna translate a 6-digit number, okay? Well, we're gonna break the 6-digit number into 2 parts, a 3-digit first part and a 3-digit second part, okay? We know how to translate 3-digit numbers, okay? Now the first part, okay, well, go ahead and translate the 3-digit number and tack on the word 1,000, and then we'll go ahead and translate the second part, okay? So that's how we're gonna do 6-digit numbers, okay? So let's take a look at refinement 5, okay? So here we go. Okay, well, let's look at what new functions we've had to add. Oh, let me kill this one off. Okay. So here, okay, translate. Okay, these are ones we've already seen before. Oh, here's translate part. Okay, so remember, we're going to take a up to 6-digit number and break it up into 2 parts of up to 3 digits each. Okay, so let's take a look at how that happens. Okay, here's translate. Okay, now you see that we do integer division by 1,000 to get the first 3 digits, and we do integer modulo by 1,000 to get the remaining 3 digits. Okay, so everybody see that? So now we have the first part of the number and the second part of the number. Okay, and again, we make sure that the first part is not greater than 999, in which case we put out an error message, okay? All right, we translate the first part, okay? And we call translate part on it, okay? The first part, and we tack on the word 1,000, and then we translate the second part, okay? And we don't add anything to that, okay? All right, and we already know ones, teens, tens, hundreds, and here's part, okay. Well, translate part is basically translating a 3-digit number, okay? And we already know how to do that because in the previous version, that's what translate was doing, right? It knew how to translate a 3-digit number, okay? So all we've done is we moved this logic into translate part, and this handling a 3-digit number, okay? So, you know, do the hundreds digit, do a teens, or do a tens digit, ones digit, and maybe put a hyphen in between them. So this logic we've seen before, except that now it's in translate part, okay? And translate itself, then job is to break the 6-digit number into 2 parts and call translate part on the first part and tack on the word 1,000, and then call translate part on the second part, okay? And remember, translate part knows how to translate a 3-digit number, okay? All right, here we go. Version 5. Okay, and oh, let's go whole hog. There we go, a 6-digit number, and it's 987,654. So how about that, okay? And you know, we can still do smaller numbers, okay? We haven't broken that. Okay, how about this is 12,345, okay? All right, so we may think that we've managed to, okay, well let's just do a little test here, okay? There should be just 100, 1,000, 10,000, 100,000, okay? Now, some of you may have noticed some bugs that have crept into our translation, and it's not a serious bug, but you know, we want one space between the numbers, and sometimes we get 2 spaces, okay? And so it doesn't look as nice, okay? Let's see. Oh, yeah, there we go again. You know, we got 2 spaces, okay? So refinement 6, which I'm not going to do, which you might look into doing, is how to get rid of these occasional extra spaces. So you want to figure out where in the program is that extra space coming from, okay? Well, here you see it's before the word 1,000. So could it be this space? Okay, but if you took out this space, then you may not be able to get a space here. Okay, so I think this is going to require a little bit of extra logic if you were to do refinement 6 to figure out how to get rid of extra spaces, and then you want to see if there are other places where the extra space shows up. Okay, we're seeing it before the word 1,000, okay, but not always. See, it didn't show up here, okay, and are there other places where it shows up? I thought I saw it. Let me try. Oh, that's probably too big. Yes. Oh. No, it did not show up this time. So there are certain types of numbers that cause an extra space to show up, and I'll leave it to you to figure out how to get rid of that space, okay? Because it doesn't always show up, okay? Those are the most frustrating problems to debug when it doesn't always happen, and you have to figure out, okay, when it does happen, what is causing it to happen, and then compare the situation to when it doesn't happen, and what's the difference? Okay, so that's a debugging challenge. Okay, all right. Any questions at all about this top-down development? Because as our assignments get a little bit more involved, I may now no longer give you an outline of the program as I have for assignment 1. And then you're going to have to come up with the structure of the program on your own. And as I said, top-down design is a very good way of going about doing it. Okay, so you start with the topmost problem, and you work your way down by breaking up your functions into smaller ones, and you get this sort of hierarchical decomposition of your problem. Okay. All right. Any comments about this? And you know, here I did it very slowly, and I talked a lot, and you know, after you've had a lot of practice doing this, it just naturally, you just end up programming that way. The worst thing you can do is to sit down and try to write the entire program in one sitting. And I know so many people try to do that, and they end up writing maybe hundreds of lines of code, and it doesn't work. And they have a really hard time getting their code to work. Okay. Now you notice that at the end of each refinement, we had something that worked. Okay, that's the key. Okay, after refinement 1, we had a working program. After refinement 2, we had a working program, and each refinement built upon the previous one. Okay, so that's another key to success, is get something working as soon as possible. Okay, remember, it didn't take a lot of effort to get refinement 1 working. All it did was read and write numbers and call a translate function that didn't do anything. Okay, we got that working, and then we worked on the translate function. Okay, and we tackled some of the easy words like the ones words and the teams word. Okay, got that working, and then refinement 3 says, okay, we're going to build on top of that and add in the ability to translate a hundreds digit, and we also did a tens digit. Okay, so we added to something that worked. Okay, refinement 4 basically took refinement 3 and added the hyphen. Okay, this was a relatively minor change. And then finally, refinement 5 took everything we knew how to do to translate a 3-digit number, and we used all that knowledge to translate a 6-digit number. Okay, so each refinement added more functionality, but it was adding it to the previous refinement that was working code. Okay, so the term is the Big Bang, and you do not want to do the Big Bang. The Big Bang says you're going to code and code and code and code, generate a large body of code, and then at the very end, you hope there's this big bang and magically your program is working. Okay, that almost never happens. Okay, so you really, really, really need to learn how to do this top-down design. Okay, all right. So I have some suggestions here for things. Other things you can do. Okay, first get rid of the space, and maybe allow commas. Allow the user to type in a number and have commas in it. Okay, so okay. All right. Any questions at all about that style of development? Okay, I hope you found it useful to see. Okay, all right. I want to talk a little bit about the notion of scope and local variables. Okay, so if you have a variable that's declared inside of a function, it's local to that function. Okay, therefore, a local variable cannot be accessed outside of the function. Okay, it's like the function owns a set of variables, it's local variables, and nobody outside of that function can get a hold of those variables. Okay, and because the variable are local to the function, that means that, okay, well, let's say you have a variable n, and it's an integer variable, and it's local to the function. It's declared inside that function. You can have another function that has a local variable n, and even though the names are the same, they're in different scopes, so they are two different variables. Okay, when you're inside the first function, you can use the local n, the variable n that's local to that function, and then later on, if you're executing inside the second function, then you can go ahead and use the n that's local to the second function, but the two local variables n have no relationship to each other than the fact that they happen to share a name. Okay, so that's the idea of having local variables. That means when you write your function, you can declare variables and not worry that some other function may be using the same variable name. Okay,
I got a question.
So, yeah.
If I'm calling, I define two functions, and I'm going to calling one of the function in another function. Like I have defining function 1 and 2, and in defining function 1, I'm going to call the function 2.
Okay.
And in this case, I'm going to define the variable in. I mean, if I define it in 1, it's still the local, and if I define it in the function 2, is it still local?
Yeah. Okay. Now the fact that you're saying that you have a function, okay, let's call it function A, and inside function A, you call function B. Is that the situation you're talking about?
Yes.
Okay. Now function A could have local variables, and function B can have local variables. And the fact that one function is calling the other function doesn't affect the scope. Okay, so the local variables of function A stay local to A, and the local variables of function B are still local to B, and those local variables can be sharing names and so forth, but it doesn't matter because they are in different scopes, even if function A calls function B. Okay, so that's a really important concept to understand. Okay, so there's several ways of saying this. We can say that, okay, a variable declared inside a function is local to that function. Okay, or you can say that the scope of that local variable is the function. Okay, so scope is kind of from the point of view of the variable. You can say that, okay, here's a variable and its scope is the function that is declared in. Or you can say that, okay, here's a function and it has all these local variables that are declared inside the function. Okay, so there are two different ways of saying the same concept. Okay, all right. And then of course the main is itself a function, and so the main can have local variables declared inside the main. Okay. Now I don't know if my program here has local variable. Oh, of course. Here's translate. Okay, and inside translate, I've got words, first part, second part. Okay, these are local variables to translate. Okay, so outside of the function translate, I cannot refer to first part or second part. Okay, these are only usable inside the translate function. And the same thing with n. Okay, so n is a parameter that's passed in, and this n is only usable inside this function. Okay, and okay, now here's another n. Now this n is different from this n. Okay, because they are local to two different functions, or you can say that the scope of this n is separate from the scope of this n because they are declared in two different functions. Okay, so there were some local variables in here. Okay, here's hundreds. Okay, this is a local variable to translate part. Okay, and and look at this. Okay, this is a compound statement. Okay, and you can see the opening curly brace and the closing curly brace, and inside this block, okay, we can have a local variable. And so tens is local. Its scope is even smaller. It's local only to within this block. Okay, so outside of this block, you cannot use tens. Okay, because see, we declared tens inside here. Okay. All right. So the whole notion of local variables and scope is important. Now, why would you do this? Well, it turns out that you only need this variable tens inside this block, and so go ahead and make it local to that block, and then you don't have to worry about some code outside that block somehow changing the value of tens, because only statements inside this block, okay, only the statements within tens scope can make use of tens. Okay, so here we can use tens because we're still inside this block, but once we're outside this block, we are not able to use tens. Okay, if you tried, the compiler will say that, oh, the tens that you have out here is undeclared because is only available inside here. Okay. Now you probably want to read about nested scopes. So here, of course, we have the scope of this function. Okay, so here is one scope. Okay, this is the scope that is the entire function, and nested inside that scope is this scope. Okay, so well, what's special about these nested scopes? Okay, well, inside here we had declared a local tens. Okay, now what if out here, okay, I had also declared a tens. Okay, so now is there a conflict? Okay, because here's tens and here's tens. Okay, well, there is no conflict because the scope of this tens is the entire function except for this block, because the block itself has a tens, and so this tens is different from this tens. Okay, and this tens is only usable inside this block. Okay, whereas this tens is usable inside the entire function except for inside here. Okay, because this local tens is overriding the inner tens is overriding the outer tens, is what I'm trying to say, okay? Now here's another thing, okay? So inside here, whenever we see the variable tens, okay, of course, we are referring to the local tens, okay? Inside this block, because there is a local tens, okay, that was declared inside here, we'll call this the inner tens. Inside this block, we cannot access the outer tens, okay? Because inside this block, whenever we see tens, it's going to be referring to the local one, okay? And so inside this block, we cannot access the outer tens, okay? Now, having nested scopes is perfectly normal. Having local variables inside of a block like this is perfectly normal, okay? But I would avoid this situation where in an enclosing scope, you have a variable name, and then in an inner scope, say in this outer scope, we have tens, and then in the inner scope, we have another variable also named tens. Okay, this is very, very confusing programming. The compiler doesn't care because the compiler treats these two tens as two different variables, but you know, to a person reading this code, it can be very confusing. Okay, so I would not have a variable name and then have it be overwritten in a nested scope. It's just too confusing, okay? But, you know, even if you're a good programmer and you never do it, you may end up looking at somebody else's program, and if they're doing it, then be very careful that you know that when you see tens here, that is the local one and not maybe one that was declared outside, okay? All right, so yes?
Just curious, if I change the value of the inner tens, will it affect on the value of the outer tens?
Nope, because they're two separate variables, see? So that's why this can be very confusing, right? See, if I had another tens out here, okay, let's put our 10, okay. And then I saw this, okay. Okay, I might think that I'm referring to this one if I didn't happen to see this, okay? Now imagine that this is part of a really large program, and you know, you may miss seeing something and get very confused, okay? So that's why I personally would never do something like this unless there was some weird circumstance. I never have an inner scope variable override an outer scope variable. It is just way too confusing, okay? All right, so I think the textbook or online, you can read all about scope, okay? It can be kind of tricky. Okay, so this is the block scope. This is where you just have a block with the delineated by the curly braces, and a block can have a local variable, okay? All right, now if we have local variables, then there's the concept of global variables, okay? And constant or variable is declared outside of and before the main and any function definition. So if we go back to our example program, okay, so here is our program, and way up here, I'm going to declare something. Okay, so int okay, foo. Okay, so now this variable, okay, because it was declared outside of any of the functions and outside of the main. See, the main has a local variable number here, okay, but foo is now known as a global variable because it is accessible from any of the functions. So inside any of the functions, we can refer to foo. I could set foo equals 12, okay? And it would be referring to the global foo, okay? And I can do the same thing in the main. In the main, I could say, you know, foo plus equals 5. And again, this foo would be the global foo, okay? Now, good programming practice says you should never do this. You should avoid using global variables, okay? And the reason is that, okay, let's say that main calls translate, and then translate goes and sets foo to 12, okay? Now, maybe main doesn't realize that when you call translate, it's going to change the value of the global variable. And so here, you're doing something with foo, and you don't know that translate had done something to it, okay? Because it's global. And same thing here. If inside another, I can't seem to find a good, okay, so let's say here, we do something else. Foo gets the value 7, let's say, okay? All right, so the problem with global variables is that the main and all the functions have access to it, and it makes it extremely hard to debug the program because now you have to keep track of, okay, who changed the value of foo? Yeah, is the main or did one of the functions do it? Okay, so you definitely do not want to use global variables. Okay, so I'm going to get rid of that and get rid of this. Okay, so if you have a value that you've calculated in one function and you want another function to have access to that value, then you want to pass it as a parameter to that function. Okay, don't rely on global variables don't rely on global variables to use as a communications mechanism between functions. Okay, you should only do it through passing parameters. Okay, all right. So global variables bad. Okay, now global constants are okay. Okay, so we could have gone up here. All right, let me put in a constant. How about const double pi equals 3.14, okay? Whoops. Okay, so now I have declared a global constant, okay? So pi, okay, I've said is constant so that after I've initialized it, I'm not going to be able to change the value of pi. It's a constant, okay? And now it's okay because whereas all the functions in the main can access pi, can use pi, none of them can change the value of pi. Okay, so then that means that having global constants is okay because, well, they're called constants because they can't change. A coding convention is that the names of constants should be in all caps. Okay, so that's why I wrote pi with all capital letters. Now, why would you use a constant like this? Okay, let's say that we have a program and we're using 3.14 as an estimate of pi. Okay, and throughout the program, we have 3.14 sprinkled throughout the program. Okay. Now later on, you decide that, oh, we really need a more accurate estimate of pi. So you change the 3.14 to 3.1415926, which I believe is a more accurate version of pi. Well, if you had sprinkled the number 3.14 throughout your program, and you decide to change that to 3.1415926, then you're going to have to find all the instances that you have written 3.14 and then change that. Whereas if you had to find a constant like this, you only have to change it in one place, because everywhere in the program, you would have used the constant pi. Okay, so then 5926. Okay, so this is why you would want to use constants, and also it makes it clearer that this is meant to be the constant pi. Okay, so global constants are okay. Okay, all right. Okay, I'm running out of time here, and I really want to talk about your assignment. So let me just do that. Okay, I'm gonna run over a little bit. I'm sorry. Okay, so this is the Monty Hall problem, and it really makes people scratch their heads because the results are not intuitive. Okay, so Monty Hall is what was a game show on TV, on American television, and the way it worked was that there was a host. Okay, this is Monty, he's the host, and in one part of the show, the host would get a volunteer from the audience. Okay, so here's the volunteer. Okay, and on the stage there would be 3 doors: door number 1, door number 2, and door number 3. Okay, behind one of the doors is a brand new car, but behind the other 2 doors is a goat. Okay, so of course, you, the contestant, the volunteer from the audience, you want to be able to pick the right door so that you'll win the car. Okay, so all right, so here we go. You're the contestant, and you say, hey, I want door number 3. Okay, now Monty, of course, knows which door, behind which door is the car. Okay, so, and let's say that he opens one of the doors, one of the other doors, and you see a goat. Okay, so you pick door number 3, Monty opened door number 1, and there's a goat. Okay. All right, so now you have a choice. Monty gives you a choice. Should you stay with your first door, door number 3, or should you switch over to door number 2? Okay, the one. Okay, now the question is, are you better off staying with your first choice? Or after Monty opened the door and you see a goat, are you better off switching to the 3rd door? Or does it matter? Okay. Now, a lot of people are going to say, well, you know, when you first start out, there's a 1 out of 3 chance that you're going to win the car. And the fact that Monty opens up one of the doors and shows you a goat, your chances should still be 1 out of 3. That should not have affected anything. Okay. And therefore, it doesn't matter whether you stay with the original door or you switch, because your chances are still 1 out of 3. Now, other people will say, oh, but look, Monty has opened up one of the doors, and you see that the car is not behind the door that Monty opened. And so does that affect your chances of winning the car? And should you stay with this door or should you stay with that door? And other people are going to say, oh, well, now your chances of winning are 1 out of 2. You know, it's either this door or this door. And again, it shouldn't matter whether you stay or switch. Okay. Now, we're going to run a simulation. So your program is going to run a simulation. And let me show you the example. And when you write this program, you should do the hierarchical decomposition that I showed you with the earlier example. Okay, so let me actually go to the write-up because there's a little bit more detail there. Okay, where is the write-up? Let's see, 180A, assignments number 2, and here's the write-up, okay? All right, so there, I explained the problem, and what your program is supposed to do is run 100 simulations of this this little scenario, okay? And each scenario, in each scenario, you will randomly place a card behind one of the 3 doors, and Monty, who knows, Monty, of course, being the computer program, will know which door has the card behind it, and then you will then have the contestant come up here and randomly pick a door, okay? Because initially the contestant doesn't know which door, and then you will have the simulation open up one of the doors that shows a goat, okay? And of course, your program knows which doors have goats behind them, and then you will then see would the contestant win by staying with the door that he originally picked, or would he win by switching doors, okay? And after 100 simulations, you'll count up how many times the contestant wins by staying and how many times the contestant wins by switching, okay? So here, your output will look something like this, okay? So here, okay, here I only did 10 simulations. For each simulation, you randomly pick a door where the car is. Okay, so here, in this case, it was 3, okay? And then the contestant randomly picks a door as his first choice. So here, we randomly pick door number 1, okay? And then Monty, or the computer program, opens up a door that has a goat behind it, okay? And now the contestant has a choice, okay? Either he can stay with the first choice or choose the remaining 3rd door, okay? And because in this case, in this simulation, because the car was behind door number 3, the contestant would have won had he switched to door number 3. So here, he would have won had he gone with the 2nd choice, okay? Now, whoops, in other simulations, okay, so here in this 3rd simulation, the car ended up behind door number 2. The contestant by random picked door number 2, okay? Monty opened up door number 1, okay? So if the contestant decides to switch, he would have switched to door number 3, okay? But in this simulation, he would have been better off had he stayed with his first choice because that's where the car was. And so here, the win would have been the first choice, okay? So if you do 100 of these simulations and count up how many times you win if the contestant stays with the first choice, and how many times the contestant wins if you stay with the 2nd choice, you'll see if in the long run, are you better off staying with your first choice, or are you better off switching doors, okay? And now using statistics, and I teach statistics in Data 220, you can prove one or the other. I'm not going to tell you which it comes out to be. You can prove that it's either better to stay or better to switch, or it doesn't matter, okay? But you're going to write this program that does these simulations, and you're going to demonstrate empirically, should you stay, should you switch, or does it not matter, okay? And the more times you run this simulation, the more evidence you'll have as to which of the 3 is better, okay? And so I'm saying do it 100 times. you can do it more times if you like. Okay. Now I showed you how to generate random numbers initially, and so you're going to have to generate a random number 1, 2, or 3 to put the car behind, and you're going to have to generate a random number 1, 2, or 3 for the contestant's first choice, and then there's another instance where you have to generate a random number, and you'll read about it in the write-up. Okay, so that's why I showed you in the beginning of the hour how to generate random numbers. Okay. All right. Is this making any sense? Now, because of the random number, the random nature of the output, because you're generating random numbers, you know, when you run your solution and get your output and compare it to my solution and get output, of course they're going to be different because of the random numbers. And so you're still going to use CodeCheck, but ignore CodeCheck's comparison of the output because, well, it's random, so there's no way to compare. Okay, so okay, any questions about this? Okay, and here this program is going to be a good enough size and good enough complexity that you really want to be sure that you use
hey, Professor.
Yeah.
So is the score matters in the code check?
No, the score doesn't matter. What the grader will do is download that signed zip file, and he'll be looking at your program, looking at your output. If the program is such that it does make sense for CodeCheck to match, then of course the grader will look and see if the output matches. But in this case, it doesn't make sense at all for CodeCheck to try to match, and so he'll ignore the score. Okay, so it's really comparing, looking at your program to make sure that you designed it well, looking at the output to make sure the output is reasonable, and only if it makes sense for CodeCheck to do an output match, only in that case will the grader look at it. Now, it turns out that in the first assignment and this assignment, it really, CodeCheck really cannot do a match. Okay. Now, in future assignments where the output is, you know, a definite output, then we'll have CodeCheck. Then we'll pay attention to what CodeCheck says about the match. Okay, so here I'm using CodeCheck mainly as a way for you to turn in the assignment, really. Okay.
Excuse me, Professor.
Yeah.
I have a question regarding the random number. We are passing time as a parameter in the SRAM.
Okay.
What is the 0 in the time?
The time 0. You know, actually, I've forgotten what that parameter 0 means. Yeah, you'll have to look it up. So look up the C++ time function and find out what that 0 means. It may mean current time or something like that. So, yeah, I guess I don't remember. I probably should have looked it up before class.
Okay.
Any other questions? Okay.
Excuse me,
yeah,
Professor. Is there any chance to have extra points assignments or make up to make up
okay,
if we
extra
lose
credit. Yeah. I'll tell you a story about extra
that would
credit.
be nice.
Yeah, let me tell you a story about extra credit. This happened a few years ago when I first started teaching, and it's actually a database class that I was teaching, and some students have fallen behind. And so I said, okay, I'll give them some extra credit so they can catch up, okay? Well, I got into trouble because when you give extra credit, you have to give it to everybody. You can't just selectively give extra credit to certain students, okay? All right, so then what happens when I do extra credit for everybody is that the students who are ahead, well, they can do the extra credit, and the students who are behind have trouble doing the extra credit, and then the gap between the two of them get worse. So I may give extra credit just because it may be a fun thing to do, but in terms of catching up, yeah, I'm not allowed to give extra credit only to certain students. Okay. Now, if you join the class late, let's say, yes. If you join,
Actually, I see your point of view, Professor. I see your point of view, not to enlarge the gap between the students.
Yeah.
But last semester, 13 out of 20, almost 65% of the whole grade was based on the assignment. If keeping that limit works for you, as well as giving extra credit to just within this limit, if it works for you, it would be really nice for the students. I mean, if the students are not gonna get any more than 65% of the course grade, at the same time, if they have any makeup opportunity, that would be really nice.
Yeah,
I
well,
don't know your strategy. Yeah.
Well, okay,
If
so
you can
as
give
I
it
said,
a-
I have to follow the department's rules, and I already got myself into trouble once already. And if I give out any assignments, whether it's makeup or extra credit, okay, well, let's just call it extra credit first. I have to give it to everybody. Now, in terms of makeup, there are makeup exams that I could possibly give. Let's say that on the day of the midterm, you're sick and you got a doctor's excuse, then I can legitimately give you a makeup for that, okay, or the final exam. But as far as the assignments go, I cannot give extra credit unless I give it to everybody. And now I may do extra credit because it's a fun thing to do, but you cannot use extra credit as sort of a catching up type of thing.
Professor?
Yes, I see.
So let's not talk about extra credit, but could you give us extra assignments which are not actually graded, but will help us understand the concepts better? So if the person does not know to code, he could learn, and then the gap lessons.
Okay. All right.
Simpler assignments, Professor.
Yeah. Okay. So, well, first of all, the practice assignments we're supposed to give you practice, but then they are graded.
Professor, I mean, for example, you taught us a program today about translations, right?
Yeah.
You broke it down into 1, 2, 3, 4, and 5.
Yeah.
So if you could give us a problem like that, and if you could help us understand to break down, not the assignment problems, something similar to them, so that we could actually learn to do the assignment.
Yeah.
Even the gap would not widen.
Yeah. Okay. Now there are problems like that online already, so you can do an online search.
Professor, the problem with online is there are too many problems there. The base, the knowledge base, it doesn't narrow it down to
okay. Yeah.
If you could find the time.
Yeah, then somebody has to grade them, and yeah. Okay. Well, I'll think about it. Or if I find a particularly interesting problem online, I'll point that out, and people can try it. Okay. So I'll keep this in mind. That
Thank you, Professor.
People want more practice in programming. Okay.
Okay.
Now, the semester starts out with me talking a lot about the language C++, and I find that necessary because it turns out that most of the students in the class are not C++ experts. Okay, I can see that from the challenge exam, that just basic C++ is something I need to cover. And so I'm trying to cover some of that. But of course, the class is supposed to be about data structures and algorithms. And so I'm going to have to start transitioning into those topics pretty soon. And then, I'll just assume that you're already a good C++ programmer, and I can talk about sorting algorithms and tree structures and just the data structures and algorithms part of the course. Okay.
Okay, so, I understand, Professor.
Yeah. Okay. Any other comments? If you have any questions about the homework assignments, use the discussion. If you send me a question, I'll just ask you to please post it to the discussion page in Canvas, because quite often the questions are questions that other students might have, and so I will only have to answer it once. And many times, once you posted a question in a discussion page, other students may answer the question before I even see it. So that's good too. Okay. All right. Well, now we are way over time, and I have not eaten dinner yet, so I need to go eat dinner. Okay. And so thank you all for coming, and have fun with Monty Hall and see if the results agree with your intuition. Okay. All right. So I'm signing off.
Thank you, Professor.
Okay. You're welcome. You're welcome. Okay.
Oh wait, Professor.
Yeah.
Were you? Was there an attendance thing today, or does?
No,
did you not do?
I didn't take attendance.
Okay.
Usually, you take 2 attendance in a row when the class meets twice a week, and I already took it the first time, so I'm fine. Okay. All right.